I think most of you will know Jean-Marc. To mind you, through his work before I met him yesterday. And in fact, of all four speakers, none of them, including Pat, had I met personally until this meeting. Isn't that amazing? But I knew their work, and particularly Jean-Marc, which I've admired very much. So over to you, sir.
Okay, thank you very much for this introduction. I'd like also to thank the organizer for this opportunity to talk at this workshop. And I will talk again about flexural waves, nonlinear flexural waves, in particular focusing on asymmetric solutions which are non-symmetric. Number of co-workers for this work: Van Tao Gao, Paul Milewski, Emilian, Olga. In fact, all of them except Paul are all here in the room. And it's very good. This morning we had a talk by Emilian, by Olga, also by Philippe Guyen, which gives all kind of a background for what I'm going to talk about, so that make my life a little easier. What I like to do is mathematically to compare flexural waves, that I will call sometime hydroelastic waves, with other classical waves, which are the gravity capillary waves, at least to compare this problem mathematically, to compare qualitatively solution, stress what is the analogy between these solutions and also the differences. Again, the classical assumption of potential flow theory: inviscid, incompressible, irrotational, gravity is always included. We'll have a free surface, which can be either a surface in which we take into account the effect of surface tension, or in fact the surface being an elastic sheet. A lot of the problem will be steady solution, but we'll talk a little bit also about unsteady solution, in particular when we talk about the stability, a little bit about the stability about the waves. So just a little sketch, really simple. The case of surface tension, you have a fluid, we have water in here, bounded about by the free surface, which is here this parallelogram in that sketch, and on top of the free surface we just have the atmosphere characterized by constant atmospheric pressure. And then we have waves which can be generated maybe by a moving distribution of pressure on that free surface. And in surface tension we get across the free surface a jump in pressure, which is just proportional to the curvature of the free surface. The other one of flexural waves, that's of course a problem, in fact a sketch that we saw exactly the same this morning in Emilian's talk. So again we have here the water, the atmosphere, and in between here the free surface is a thin elastic sheet, and again we would have waves generated by maybe a moving disturbance. This picture here, the previous one was a three-dimensional picture. This is here the case of the two-dimensional flows. In fact, for the first part of the talk, we will concentrate, in fact, on the two-dimensional problem and say a few things about the three-dimensional waves, not too much because Olga talked a lot about them already. So two-dimensional flows. In these two-dimensional flows, if we just look at waves independently of the way they're generated, there are essentially two basic types of solutions: periodic solutions, in which the solution repeats itself periodically with some wavelength lambda from -infinity to +infinity, and what we refer to as being solitary waves, which means in fact essentially solutions which are waves which are non-periodic, and which usually can be obtained by having these periodic waves, this layer of the fluids, when the wavelength takes the limit, the wavelength become very large compared with the depth. Now solitary waves, the classical thing is that when you don't have surface tension, when you don't have an elastic sheet, and then the solitary wave are this classical solution which is simply a hump. This is the thing which is described for small amplitude as a solution of the quarter-wave de Vries equation. But as soon as you put in this problem either surface tension or the elastic sheets, you don't get solitary waves which look like that. You get solitary waves which are one of these three types. The first type here are again solitary waves the two bottom that we have here, with in fact oscillations in the far field which decays ultimately. So the free surface is again flat in the far field. In the other one, the one at the top, that's what is called a generalized solitary wave. It's not really a true solitary wave, it's really because the free surface is not flat in the far field. You have a train of ripples of constant amplitude in the far field. So we're going to talk about this different type of waves. Again, something we've seen in this morning, but useful to remind the basic formulation. So we write the velocity vector as the form of the gradient of a potential function, which satisfies Laplace equation. I put here the formulation for simplicity, again in the two-dimensional case, and also in the case of steady solution. So Laplace equation in the flow domain, the kinematic boundary condition on the unknown free surface y equals zeta of x, the kinematic boundary condition on the bottom, and here's a dynamic boundary condition on the free surface. The case of surface tension, when you have a jump in pressure proportional to the curvature across the free surface, then the dynamic boundary condition is of this form. G is the gravity, T is the surface tension, rho is the density, and kappa is just the curvature of the free surface. In flexural waves, if we use the same models, the Toland-Plotnikov model that was used intensively this morning, then simply mathematically the blue term that we have here is just replaced by this more complicated term when S is the arc length and kappa again the curvature of the free surface. So both problems is the same type of problem. What appears in it is that either by surface tension or by in fact the flexural wave, when this constant d here is a flexural rigidity, we have in the dynamic boundary condition higher order derivatives involving the shape of the free surface. Higher derivatives, in fact, in the case of flexural wave, because we have a fourth order derivative which appears in that equation. We're going to see that there are, in fact, non-symmetric solutions. I'm going to define that in a minute. New waves that we found recently, and that these non-symmetric waves, in fact, occurs for periodic wave, for solitary wave, and for generalized solitary waves. And let me try to clarify that. If you look at all the pictures, the sketches of the waves that I put so far, they were all symmetric waves. Symmetric wave means that you can find a vertical line with respect to which the profile is symmetric. Like, for example, this wave here is symmetric with respect to this axis. This solitary wave is also symmetric with respect to this vertical line. And it's not that surprising intuitively that you get symmetric solution. After all, this potential flow theory, so you can always reverse the direction of the flow, so you would expect symmetric solution. Even theoretically, if you list an interesting paper in 1988 by Craig and Stenberg, when they took the case of the solitary wave with just gravity, no surface tension, no elastic sheets, and they prove, in fact, that the solitary wave have to be symmetric. There are no non-symmetric waves, but there are no similar or equivalent theorems when you have surface tension or when you have flexural waves. And in fact, what we have in here in the talk is numerical evidence that, in fact, non-symmetric waves do exist in that case. Okay. The numerical method, especially for non-symmetric waves, it doesn't really matter which method. You have to use an efficient and a good numerical method. But the difficulty is not so much in the difficult method, is in order to, if you're going to solve ultimately the problem by using Newton method, it's a question of the initial guess. You have to be able to have if there are non-symmetric waves, a good initial guess which is going to give you a non-symmetric wave. If you don't have such a good initial guess, it would diverge or go back to a symmetric wave. And this is it will be found, we'll see here, by following branches of symmetric waves, and then we have a symmetry breaking, and then we can get on this particular branch, or then we have clever tricks to generate the initial guess. Continuation method I use intensively, meaning that if you're lucky to find a non-symmetric wave, or finding any kind of waves, then by continuation you can find the whole branch of solutions which goes through that solution. simply using that solution as an initial guess. When you perturb slightly the parameters, find a new solution, modified again slightly the parameters, and build like that families of solutions. So we're still in the two-dimensional case. We're going to start with this wave with decaying tails. There are two types of waves that are presented here. The top that we would have here, like this, is a good name for it, and we use that name. It's an elevation wave. And the one that we have at the bottom here of the slides, this is what is referred to as being a depression wave. Okay, that's an obvious description of these waves. Oop, going the wrong way, no? Yeah, not going the wrong way. I wanted again, like what Emilian did, put again the nonlinear equations, and some preliminary insight into that problem can be gained by linearizing the equations. You can see that the trivial solution of that problem is phi equal to, in fact, ux, when u is a constant. It's just a uniform trim with a constant velocity, and zeta equal to 0. Look at the solution, like on top that we have here, as being a perturbation of that trivial solution. Goes with a simple calculation, and that would lead, as Emilian showed, to the dispersion relation associated with these waves. Now, in the case of surface tension, the dispersion relation is that g over k, t over rho multiplied by k hyperbolic tangent of kh, a classical dispersion relation of linear gravity capillary waves that we learn in elementary courses. If you go to the same exercise for the linear flexural waves, essentially the only difference is that this k is replaced by k to the power 3. And what I want to do that, I just rewrote these two relations in red in this form, the two formula in blue, simply, in fact, by introducing some dimensionless variables, introducing the fluid number, introducing some dimensionless wavelengths, and this relation gives, in fact, in both cases, the fluid number as a function of L. You get a different curve for different values of, in fact, tau, the bond number, which involves the surface tension, and different curves for different values of beta. The thing to stress that we have here is that these curves, if you plot now this value of f squared versus of L, then this curve would have a minimum for some values of L. In fact, in the case of gravity capillary wave, if tau is smaller than a third. For flexural waves, you always get a minimum whatever the value of beta is. Now, these waves that we would have here will turn out, if they exist, to bifurcate, in fact, from this particular minimum that we get there. And that comes intuitively because at that particular point, when you have the minimum, according to linear theory, the groove velocity at that point is equal to the phase velocity. So this is this value C min, which was referred to by the speakers this morning. So let me compare that first the case of gravity capillary solitary waves, so these particular waves, and then compare these results with the corresponding solution for flexural waves. I will describe that in water of infinite depth, but what I'll do in the next few slides qualitatively is the same in water of finite depth. So what we have two types of solutions. We have these elevation waves, and then we have these depression waves. So we have a branch of solution associated with the elevation wave and a branch of solution associated with the depression wave. I defined here some kind of an amplitude, which I call here on the slide the value of zeta at 0. That's the vertical axis. That's essentially the amplitude of the wave. And in here, it will be positive for elevation waves and negative for depression waves. So I put this amplitude on the vertical axis on these two particular pictures, and on the horizontal axis, I put the speed at which the wave is moving. The waves bifurcate from C min, so the point that we get in both cases that we have there, this point that we have here corresponding to well, better explain it on this one. This point that we have here in here for zero amplitude, zero value of the amplitude, correspond in fact to, in dimensionless variable, to the C minimum. And then what we have here, we have the branch of depression wave with zeta equal to 0, which is a rather simple curve. It's just monotonically decreasing. These are the depression waves. The elevation waves is this branch that we already saw also this morning. The branch, in fact, of elevation waves is rather complicated. It turns around and turns around. It's all kind of zigzag. We stop here at that point, but it would continue to do that. A very complicated curve, much more complicated for the elevation wave than the depression wave. This is the same picture. Again, we have the speed c on the horizontal axis, but then we put on the vertical axis that we have here the energy of the wave. I'll put a definition of the energy. And again, we have something which is similar. I mean, we would have here the blue curve that corresponds to the depression wave, a simple curve, and then a more complicated wave curve corresponding to the elevation waves. Now, on these kind of waves, there's a lot of work which has been done for many years. A lot of it is by a number of people who are sitting in this room, theoretical work. There have been, before the result that we presented here, previous results on non-symmetric waves, but most of them were derived from model equation, like the fifth order quarter-wave de Vries equation. What we have done is to show this existence, provide numerical evidence of these type of solutions for the full Euler equation. Now, the basic idea to find these non-symmetric waves come from, again, looking at this picture that we have here. Well, we see here that we have the depression wave and we have the elevation wave. It is possible to find an elevation wave and a depression wave corresponding, for example, to the point A and B, which are both traveling at the same speed. It's also possible, because of this complicated zigzag things that we have here, to find several elevation waves that we have here, which also travel at the same speed. Now, the non-symmetric waves, in fact, are obtained by combining these two waves that we can travel at the same speed. It's a little bit like adding them, but it's not that, because it's a nonlinear problem. But it's what we do numerically. We build, in fact, an initial guess which consists of gluing together two waves which travel at the same speed. And then, if we do that smoothly, we have a good initial guess, and doing the iterations, then it converges to non-symmetric solutions. And then we use continuation to find the complete branch of solution. This is an example of that. This corresponds, in fact, to the point A and B that we had there. So this is obtained, in fact, by gluing together a depression wave and an elevation wave which travel at the same speed. And then we have the whole branch of solution. Now, when we follow the branch of solution, we come to find that the non-symmetric solution that I'll show on the next slide, in fact, bifurcate from branches of symmetric solution. So the dotted curve that we have here are branches, in fact, of symmetric solutions. And then we have here two bifurcation points. And from this point, we have a symmetry breaking. And then we get that branch of solutions. It goes here. It has a sharp turn here and come back here. So it starts from a branch of symmetric waves, and it ends up on another branch of symmetric waves. So that illustrates again the picture here that we do here. So the first picture that we have here is, in fact, how we built the initial guess. This is an elevation wave that we have here. This is a depression wave. Both waves travel at the same speed, and we glue them together, use that as an initial guess, and like that we're able to jump on this branch of non-symmetric wave that we described there. And if you go and look, for example, at this picture that you have here, you can see you have different. It's in fact a non-symmetric wave. You can't find a vertical line with respect to which the wave is symmetric. So if you reverse the direction of the flow, you get another solution. That's what it means in other terms. And then that's the end of that branch. We end up again with a symmetric solution. You can do the thing and the same thing by starting with two elevation waves traveling at the same speed. There's a lot of different possibilities because of all this zigzag form that we had in the dispersion relation. Again, we did some, for example, from the wave C and D. They're very close to each other, but travel on the same speed. The wave E and F. And the branch of solutions are something which are very, very complex. They start, again, on branches of symmetric waves, and then you get this complicated structures. It was very time-consuming to calculate that, which are, in fact, all these complicated branches of asymmetric solution that we tried a little bit to clarify here by putting a few blow-up of these solutions, and that's even a worst case that we have there. But again, illustrating the things, here we have two elevation waves that we glue together and then construct the branch of solution and end up, for example, with these complicated waves that we have there. Okay. Now, go back to the hydroelastic waves. We want to look, in fact, at these waves that we have in here, but for flexural, the word for hydroelastic waves. This is joint work with Tao and Zan, and there is also some work of Philip Guillen and Emilian Perrault that was described on that. You could recognize some of the things was described this morning. What is the situation? For hydroelastic waves, you still get, we had that story this morning also, a minimum in the dispersion relation. Now, if you go to a depth which is infinite depth, or a depth which is rather large, what you get is, what you get is again waves which bifurcate as C min, but they don't bifurcate from zero amplitude. As you can see here, they bifurcate from this point and from this point, so they bifurcate, in fact, at finite amplitude. If you go to the thing and reduce the calculation for flexural waves, by go to very shallow water, then again, you get a situation in which the wave, the elevation wave and the depression wave, bifurcate from C min, but at zero amplitude. So the shallow water for flexural wave, in a sense, is similar to what we had for gravity capillary waves. And that's consistent, as was shown this morning, with NLS, because well, I guess in this case, they're looking if NLS is focusing or defocusing, as was explained this morning. So that is the main difference that we get between the gravity capillary waves and the flexural waves that we have there. We see here that in the picture, apart from the fact that it bifurcates at small amplitude, we again get a complicated zigzag curve for the elevation waves, and in fact a monotonic curve for the depression waves. The zigzag thing that you get here, when it bifurcates from A small, it bifurcates from zero amplitude, but for the elevation wave we don't see that zigzag behavior in the curve. What's happening in that case, related to the fact that we have, in fact, rather shallow water, is that when we move to the branch, then in fact the trough of the wave is approaching the bottom and would at some stage touch the bottom. So you have a touchdown singularity. And that would be illustrated on the next picture when I'm going to show, what is that? The profile corresponding on the picture to the point A and B. Now the depth, in fact, the h in that problem, which is the depth, for that problem was taken as being h equal to 2. Well, what happened to that picture? It's gone. Very bizarre. Okay. These are in fact the two pictures corresponding to the point A and B. And we can see here that the lower points that we have here tends to approach -2. So in fact, I'm getting the zigzag curve is get cut because the branch stops because the free surface is in fact hitting the bottom, and when the trough is approaching the bottom, the numerical procedure fails in that case. What else want to say about that? I just put a slide on that. In this case, which is a case of either infinite depth or rather deep water, so the branch of solution do not bifurcate from zero amplitude, but in that case there are other type of solutions which did not in fact exist for gravity capillary waves. They are in fact dark solitons. And this is just, I'll just put a slide showing a computation of these dark solitons in that case. Stability of the wave is rather complicated. I'm going to describe it in terms of the energy. I said that I will put a definition of the energy that I already mentioned. This is the energy in the case of flexural waves. There is a term here which is the kinematic energy, and then the potential energy due to gravity and due to the elastic sheet. And I just put that. We saw in fact part of this picture this morning also. This picture is for the depression waves, showing in fact the energy that we had on the previous transparency versus the speed c. And then by using a time-dependent codes, we did study the stability of these waves. Now, the part of the curve which are not the solid line are part of the curve for which the wave are unstable. There's only a portion of the curve for which the wave is stable. Do the same thing for the elevation waves. Again, the energy versus speed, we get a complicated curve. But again, in that case, only a portion of the curve that we have here, we found only that a portion of the curve is stable. I'll try to see what we have there. I had another, they got a little mixed up. We did study and try to find non-symmetric flexural waves, and we were able to find some. Now, if the water, I'll just show you here the results which are in fact in shallow water. And this is an example, again, of non-symmetric waves, a flexural wave that we have here. There's no vertical line with respect to which is symmetric, and this profile corresponds to the 0.5. The interesting thing is again that the branch of solution that we have here bifurcates and emerge by symmetry breaking from a branch of symmetric waves. So that's one of the things that we have there. Generalized solitary waves. So we're now talking about waves which have infinite depth, which have a train of ripples of constant amplitude in the phi field. First, I didn't think that there would be non-symmetric waves, generalized solitary waves, but in fact, we were able to find some of them. So first, that's just a picture to show how we calculate this generalized solitary wave. In fact, that's not what we're doing, really. What we're doing, we calculate, in fact, a very long periodic waves. We increase the wavelengths, and when you increase the wavelengths, well, you can see that these waves tends to approach, in fact, a generalized solitary wave. Now, these waves on that picture are all symmetric waves. They are all symmetric with respect to a vertical line here at 0. Now we did calculations and found some non-symmetric one. I'll just show pictures illustrating that. For example, the picture that we have here with a blow up of that particular solution is a non-symmetric wave. It's not very non-symmetric. To show that, I just put an horizontal line, in fact, through that trough that we have here, and you can see here that the other trough that we have here is not on that line. So it's a little non-symmetric. Some of them are more drastic in the non-symmetry, like for example the one that we have here on this particular picture. No vertical line with respect to which the wave is symmetric is surprising, because still if you go far away, the ripples that you get in the far field have the same amplitude on both sides. But in the middle, you get these waves which are non-symmetric. A very recent result, which came by using our time-dependent code, was to try to excite all kinds of different waves. And we were able to excite, in fact, one of these generalized solitary waves. This was obtained by time-dependent code by putting some suitably well-chosen distribution of pressure on the free surface for some time, and then to release that distribution of pressure and to let, in fact, the free surface evolve. And interestingly, if you look in here, first, it evolves in here, you get two depression waves, and in this case here, you can see here that you have something which looked like a generalized solitary wave. In fact, by taking the parameter corresponding to this, we did compare that part of the profile that we have here with a generalized solitary wave, calculating in the usual way by using the steady code, and we in fact found a reasonably good agreement between in fact the red curve that we have here, which is a steady generalized solitary wave calculated with a steady code, and the black line, which is what is produced by the time-dependent calculation. Interesting to see them emerging in that. I said that I would present also non-symmetric periodic waves. I'll present them in the case of gravity capillary waves. Something similar could be done for flexural waves. There was, in fact, previous work on this topic. They look a little bit like what also was mentioned this morning, the classical, by Olga, she talked about the Wilton ripples. Wilton ripples are gravity capillary waves, which are dimples on the free surface. That's one of them. But all these waves, these classical waves, are in fact symmetric. You can find a lot of vertical lines with respect to which the profile is symmetric. And again, by following branch of solutions, we were able to identify all kinds of non-symmetric waves, which are periodic. So this is just a period of it. There is no vertical line with respect to this funny thing is symmetric. All kinds of waves which are like that and which are in fact non-symmetric. And interestingly, some of these branches of solutions form in fact kind of Azola closed curve in parameter space, as illustrated on this picture. Three-dimensional flexural waves, well, we had a nice talk by Olga this morning, so I'm not going to repeat the same kind of things. What I like to do, and to add something, is that we were asking the question, can we find, in fact, asymmetric three-dimensional waves? And we look at it in the case of gravity capillary waves. Now, we did that before, and I showed the result for two-dimensional waves. To do this calculation, it's already something which you need a lot of mesh points, thousands and thousands of mesh points. It was already very time-consuming to do the calculations. So we could do it in principle for three-dimensional waves, but we felt lazy not to run the thing for hours and hours. So we did something a little similar. We used a model, which is shown to be a very good model for three-dimensional waves, which was developed by Akes and Milewski. And for these models, the computations are not that expensive. And at least for that particular model, we were able to find non-symmetric waves. So this is a three-dimensional waves, and it is non-symmetric. So it gives evidence that these type of things exist also in three dimension. So all the three-dimensional waves, I mean, for these things, I mean, the equivalent, this is something which was just in the plane. When you get to the three-dimensional case, you get this time of picture, in fact, in the middle plane, in the direction of the wave propagation. In addition, if you go perpendicular to the board, then you get a monotonic decay. So it's a bit also it's the non-symmetric waves. You get these oscillations in the direction of propagations, and then you get monotonic decay in the direction perpendicular to the direction of propagation. It's another example of such asymmetric, non-symmetric, three-dimensional waves. So in the conclusion, I presented a lot of waves, a lot of new non-symmetric waves, solutions all over the place, branch of solutions all over the place, and you got some reference where you can find some more information on them. So I think we have enough waves, so.
Question time. Question or comment? I have a quick one.
Okay.
And that is, in reading your paper, it's three-dimensional. If you read my linear stuff, that's two-dimensional. So you've got to do a map from 3 to 2 and from 2 to 1. Just terminology, right?
Oh, okay, okay. Yeah, that's right. It's depend on, yeah.
So I was thinking the thing in the plane is against the thing in the...
Yeah.
You've got one plane here, but when we were looking at patterns, that was across the horizontal plane.
Yeah, that's
So
right.
I call that two-dimensional. And one-dimensional, right?
It's true that when you solve a two-dimensional problem, at the end you solve a one-dimensional thing.
Terminology.
So, yeah.
Yeah, Jean-Marc, can you say again what mechanisms there are in the ice model? And how realistic?
What kind of a...
Well, you had some boundary condition for ice.
Yeah.
Could you say a few words about that?
Yeah, application.
Well, the boundary condition there, the only difference was the dynamic boundary condition, in which you get these high-order derivatives which appear in it. So it's just to find, to develop it, to find what is, well, in both problems, in fact, what is the pressure which is exerted on the fluid. Now, surface tension, that's just a constant pressure on top, plus the jump due to the surface tension. And then the elastic sheets, you get that pressure. Now, there are different models which can be used for that. There are, instead of all these complicated terms, for example, what was it? You can get something with the second derivative respect to x, I guess, of the curvature. That is the KL model that was described in this morning. In fact, some of the calculation that I showed was for this particular model. And now all the models are equivalent if you go and linearize this part of expression. This expression, you get the fourth derivative of eta.
How realistic is it? Is anybody trying to make it more realistic?
Realistic and observation, is it?
Yeah.
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 Well, there was some comparison that when Emilian presented this morning, with waves like that were kind of observed. And, it's more realistic. I mean, all these things for gravity capillary waves. If you use water, usually you cannot observe them because either you have to take very small depths, or these ripples are kind of damped. There are examples that of these kind of gravity capillary waves which were observed, but usually not with water, with mercury and things like that. Now the possibility to maybe more observe these flexural waves in experiments.
Question here.
Yeah, well, thank you for an excellent and also very entertaining lecture.
Yes.
Thanks.
So your main point is that you can find asymmetric waves.
For what?
The main point is these asymmetry.
Yes, that's right. That's
So,
surprising.
so if you didn't know about the numerical results,
Yeah.
but if you were very clever with the mathematical structures of the equations you put up on kind of your first slide,
Yeah.
which term in, or which terms in this flexural gravity combination makes this asymmetry possible?
Well, it's a term like the surface tension term, or the one with the flexural
Yes.
rigidity. Because if you remove these terms, then you can prove that waves have to be symmetric, for example, like
That's
solitary.
all. That's all. So then you know in advance that you will find it.
I never saw. Maybe there is some theoretical evidence of that. Well, what that doesn't exist is a proof that these waves, with flexural waves or gravity carrying waves, have to be symmetric, and they don't seem to be, from what I've shown, to be the case. It's
But is it the second derivative or is it the cube?
I think
That's right. Can you put that slide?
no, I don't think it's a cube. No,
It shouldn't be.
because you can. I think we tried a little bit that you could get these non-symmetric waves. Correct me if I'm wrong, with the KL model. I don't see why, which doesn't have this kappa cube.
Here we only have depression wave.
Yeah. Yeah, oh, I see. We only have depression
we
wave.
don't
Yeah,
have-
yeah. So we need to have the other one. Yeah.
Yeah, we need a very complicated problem
Yeah.
for symmetric waves.
But you can certainly get the non-symmetric wave for gravity capillary waves, and then you don't have something like the K cube, the kappa cube, whatever. Yeah.
One more here.
Yeah, so interesting talk indeed. The total layperson's question. Okay, I'm not even in this workshop, and you talk about this nice non-symmetric solid waves and stuff. But can you make prediction about how energy can be pumped to produce them, and what is their lifetime? Can that be something that come out of your calculations that probably have more practical sort of
Well,
to people?
how it comes in a time-dependent codes or something like that. I talked a bit about stability and show that some branch of solution are stable. But what I was talking about is about the symmetric waves. Now we were curious about that. What about the stability of these non-symmetric waves? So there are a lot of them, so we couldn't study that, but we did some experiment. We saw, for example, that a good candidate for stability would be for this type of waves if the building blocks that we're using here are in fact stable, and put them together. But unfortunately, in all the experiments, they were found to be unstable, to go back to things like symmetric waves. So the time life is zero, probably.
One more question.
Oh, yeah, I was just gonna comment. So when you saw these asymmetric waves, right? Are they higher up on the higher amplitude? Do they go from zero, or they go from some non-zero amplitude? Like the
Non-zero,
bifurcation branches.
non-zero.
No, not zero. Yeah.
Okay, so there's some nonlinearity already, right? So you can't just. So the question before asking which part of the is it the flexural term or et cetera, like that contributes to this asymmetric waves? It's a bit of a strange question, right? Because that's a linear theory question, maybe. So, and you need some nonlinearity to get the.
Yeah, you need some linearity because
Yeah, so you can't really
when it
say that.
bifurcates from finite amplitude. Oh yes.
Right, okay. So you can't really say that, it's the particular form of the flexural term that contributes necessarily, because you need some nonlinearity. So you can't, yeah.
Yeah, but you have also nonlinearity from the rest of the problem. Yeah.
Yeah, exactly.
Yeah.
Okay.
Question.
If water wave are wave of small amplitude, close to linear theory, usually they are obtained via bifurcation theory, yes? And we can expect that they are symmetric, yes?
They're symmetric. Yeah.
And there exists a branch continuous to higher magnitude.
Yeah.
Along this branch, we can expect that they are all symmetric, yes?
Uh-huh.
But at some moment, we have non-symmetric waves.
Yeah.
It is bifurcate from this branch.
Yes, exactly.
Exactly.
So that's exactly what you say. You have a branch of
nowhere.
symmetric waves, So you move on it, and at some stage there will be another branch of non-symmetric wave which bifurcate from it.
Secondary bifurcation.
Bifurcate from non-zero amplitude.
Yeah.
Yes?
Yes.
Yes.
Yeah.
There's only isolated branch which they can exist from nowhere.
Therefore, these things very difficult to discover theoretically, only by computer calculations.
So that's what we had. You did this branch of symmetric waves,
Yes.
and then we had this non-symmetric at some point. It bifurcates, it does all kind of things, and then come back to another.
Oh.
There's a symmetry breaking, yeah.
There is some kind of non-uniqueness, yes? Non-uniqueness of the solution, bifurcation.
Yep.
Yeah.
Yeah.
To the other.
Of course, a lot of non-uniqueness in it. Yeah.
All right. Any further questions? If not, then we thank you for.
Okay.